Welcome to Early Earth Evolution and Spherical Harmonics. An introduction, Spherical Harmonics and Rayleigh-Benard Convection. In this presentation, we will be building a model, and as John Holland, 1998, points out, that the whole process of model building starts when our attention is attracted to some complex pattern in the world. This is exactly the case for the research results presented here. These patterns will produce multiple tracks of evidence supporting our model. Spherical harmonics, a powerful tool. This tool will assist in creating a model that helps explain the observed patterns. So what are spherical harmonics? They are foundational tools across mathematics, physics, computer science, engineering, and other disciplines where the problems include a sphere. This approach is especially useful in such studies as earth sciences. Spherical harmonics are orthonormal, that is, at right angle, basis functions defined on the sphere, such as point P in the image below. They originate from the solution of Laplace's equation in spherical coordinates, providing an essential method for representing functions on spherical domains. Here we can see the various types of spherical harmonics, that is, zonal, sectorial, and tesseract. You may have noticed in the previous slide that below each of the titles of the various spherical harmonic types that there were two numbers inside of parentheses. The first number is the L value, which represents the number of latitudinal oscillations from pole to pole. The second number is the order. M represents the number of longitudinal oscillations around the equator. In essence, the degree L determines the overall complexity of the function on the sphere. The order M determines how many times the function oscillates around the sphere's equator. This slide scrolls through rather rapidly the various types of spherical harmonics. We will be using sectorial harmonics primarily as a tool to analyze various data sets. As an example, we can see Vaikolainen et al. 2014 using sectorial harmonics here to analyze the geomagnetic field of the Earth. Even though we have illustrated visually what a sectorial harmonic is, this definition is instructive. Sectorial harmonics are a type of spherical harmonic where the parameters L and M are equal, that is, L and M in absolute terms are equal. This condition causes the spherical harmonic to oscillate only in the longitudinal direction, that is, around the sphere's axis, creating a pattern resembling, quote, vertical orange quarters. The functions are defined by a single parameter, L or M, as there is no difference between the latitudinal and longitudinal variations. The pattern resembling a vertical orange quarter is presented and developed further later on in this presentation. Spherical harmonics and the insights of geophysicist Vinnick Mines. In 1951, Dutch geophysicist Vinnick Mines discovered, quote, a possible correlation between the topography and mantle currents. He found that the Rayleigh number of mantle currents, which dominates their probability, depends only on the order of the spherical harmonics. The mantle currents mentioned in this quote are Rayleigh-Benard convection. Vinnick Mines plotted spherical harmonic order against topography. This graph is shown in the next few slides. He noted how remarkably regular this curve is, and this regularity showed him that there must be a physical cause behind it. The model that we are developing here will show that this insight by Vinnick Mines was indeed prescient. The regularity that Vinnick Mines saw is hyperbolic, represented here by the red dashed line. However, we can see that in the first four harmonics in this graph, that relationship breaks down, and that primarily the breakdown is due to the strength of materials. For instance, at the 30th spherical harmonic, the rocks have sufficient strength to support an elevation of 200 meters. However, this would not be the case for spherical harmonic 3. The reason being is that at these lower spherical harmonic orders, the Earth is more like a mound of sand than as a solid rock. Another important consideration in respect to these early harmonic orders is that they are grand scale features that occurred very early on in Earth history. And these grand scale features were modified, if not destroyed, by subsequent harmonic orders. The various peaks along the hyperbolic curve are important in understanding the model developed here. For instance, the peaks at 5, 7, 10, 14, 17, 21, so forth. We will show that each of these peaks is a sectorial harmonic. Spherical harmonics and the Vinnick Mines model. The red column in this table is spherical harmonic order, and the various spherical harmonics, 5, 7, 10, 14, 17, so forth, are the peaks along the hyperbolic curve. As mentioned previously, Vinnick Mines had discovered the relationship between spherical harmonic order and Rayleigh-Benard convection in the mantle. However, as discussed in the next few slides, Vinnick Mines seemed to be unaware of the relationship between Rayleigh-Benard convection and aspect ratio 2. The importance of the aspect ratio in a convecting mantle. This straightforward relationship between the depth of the convecting layer and the horizontal dimension of the convection cell is well established by both numerical and laboratory simulations of convection in the Earth's mantle. As Anderson 1989 and Manville 1990 show, the most efficient way for the Earth to dissipate its internal thermal energy is through convection cells that have a lateral dimension, that is a wavelength, twice the depth of the convecting layer, that is aspect ratio of 2. The universality of self-organized systems manifesting as Rayleigh-Benard convection was brought directly to the author's attention recently when he prepared his breakfast. This is now called the Robinson polenta model and is shown in figure 4-7. He noted 5 things before eating the cereal. 1. The centers of upward movement of the convecting polenta form a regular pattern. 2. The centers consist of an outer rim and an inner depression, essentially creating an annulus in plan view. 3. The mean distance between the blueberries, the centers of the upward movement of the convecting polenta, is 46 millimeters. 4. The mean depth of the polenta is 23 millimeters. And 5. The aspect ratio for the individual convecting cell is 2. The individual cell is on average twice as wide as it is deep. Acknowledging the importance of aspect ratio 2 in respect to Rayleigh-Benard convection allows us to modify the Venick-Mines model to the Venick-Mines-Robinson model. Using sectorial harmonics, we are able to determine the wavelength for each of the spherical harmonic orders. For instance, at spherical harmonic order 10, the wavelength is 4,000 kilometers because the Earth is 40,000 kilometers in circumference. And as Venick-Mines concluded, each wavelength represents the diameter of a Rayleigh-Benard convection cell. And now, being aware of aspect ratio 2, we are able to calculate the depth of Rayleigh-Benard convection in the mantle at various spherical harmonic orders. So the 10th spherical harmonic order with a wavelength of 4,000 kilometers would have a calculated depth of Rayleigh-Benard convection of 2,000 kilometers. Let's now compare the calculated depth of Rayleigh-Benard convection in the mantle with the known depth of discontinuities from seismic data. For instance, at spherical harmonic order 10, the aspect ratio calculated depth of Rayleigh-Benard convection would be 2,000 kilometers. This compares with a known depth to discontinuities from seismic data of 2,100 kilometers. There is no doubt that the two methods of determining the depth to discontinuities give similar, if not identical, results. There is also no doubt that there is a cause behind the hyperbolic relationship between spherical harmonic order and topography gravity of the Earth. That cause is Rayleigh-Benard convection originating at various discontinuities in the mantle. Before moving on, please note within the consensus column, the blue column, the numbers at the bottom of the column, 400, 220, 60, and 20 kilometers. These values for discontinuities are beyond the spherical harmonic order determined previously by Venick-Mines. These 4 known depths to discontinuities arise from wavelengths of 800, 440, 120, and 40 kilometers respectively. and each spherical harmonic order can be recognized by 50, 91, 333, 1000, respectively. Note that the discontinuities between the 30th and 1000th spherical harmonic order are well documented. They are named after famous geophysicists or by mineral transformations. Before proceeding, I would like to point out that at spherical harmonic order 21, Zhang, 2023, published a paper giving considerable evidence for a 1,000-kilometer mantle discontinuity under the Pacific. It seems likely that the various blanks we see in the names of discontinuities column will be filled out, completed in the future. Proposed cross-section of the Earth with convection at various spherical harmonics and known discontinuities. The image to the left is a cross-section of the Earth at spherical sectoral harmonic 30. In our model, each single Rayleigh-Bernard convection cell is represented by two circles. So in this model, there are 60 circles representing spherical harmonic 30. The depth into the Earth delineating the spherical harmonic 30 convecting layer would be 670 kilometers. This is a well-documented discontinuity known as the répété or upper-lower mantle discontinuity. The 30th spherical harmonic is shown in the right-hand cross-sectional of the Earth as slightly darker. Here we show, again in the right-hand image, cross-section of the Earth, spherical harmonic 7, the Rayleigh-Bernard convection, creating that harmonic which would arise from 2,890 kilometers depth into the mantle. One can see in the inset that the red bars represent the known discontinuities from seismic data and the gray lines, the discontinuities as defined by the Venneck-Mines-Robinson model. Spherical harmonic 7 has special significance because the Rayleigh-Bernard convection cell arises from the core mantle boundary. Before proceeding, I would like to mention that the circles here representing Rayleigh-Bernard convection are merely models. The actual movement of Rayleigh-Bernard convection within cells in the mantle would not be circular. This is a model. Torsvik et al., in their 2010 paper titled Diamonds Sampled by Plumes from the Core Mantle Boundary, indicate the significance of spherical harmonic 7 Rayleigh-Bernard convection. The hotspot location of spherical harmonic 7 on the surface of the Earth would be the location most likely to contain diamond deposits. Spherical harmonic 1. Listed here are the 9 lines of evidence converging and proving the presence of spherical harmonic 1 in early Earth evolution. Number 1. Dipolar magnetic Earth as evidence of one great Rayleigh-Bernard convection cell. Here is spherical harmonic 1 as presented by Venick Mines 1964. The red arrows indicate the direction of mantle flow. Here is a more likely orientation of spherical harmonic 1. Magnetic evidence for this model is presented by Vaikolainen et al. 2014. Quote, our analysis provides a synoptic view of the Precambrian geomagnetic field, most importantly showing that the long-term average of the field is close to that expected from a simple geocentric axial dipole model. Michael et al. Go on to say that, quote, our study supports hypotheses of a strongly dipolar geomagnetic field in the early history of the Earth, possibly as a result of the absence of a solid inner core. We present evidence for the evolution of a solid inner core later on in this presentation. Gravity and the dipolar Earth. Number 2. Gravity anomalism, positive at the North Pole and negative at the South Pole. Bouguer gravity anomalism at the poles. A Bouguer gravity anomaly is a measure of the difference between the observed gravity at a specific location and the expected gravity based on local topography and density. It's essentially a way to isolate gravity variations caused by density differences within the Earth, rather than being due to altitude or the surrounding terrain. The first thing to note is that there is a 400 to 600 positive plus milligal gravity anomaly at the North Pole. This major geophysical feature covers tens of thousands of square kilometers. The second thing to note is that at the North Pole there is a distinctive pattern, which will be revealed in the next few slides. That pattern is radial. The positive gravity anomaly and the radial distribution pattern support the model being developed here in respect to spherical harmonics 1. The lack of continental material and the fact that the ocean is 4 kilometers deep at the North Pole indicate that the rocks must be more dense. Those more dense rocks on the ocean floor are likely to be mantle material, peridotites. Number 3. Peridotite mantle rocks rising northward, topped with slag-like sialic material. As Johnson et al. 2022 point out, quote, Earth is the only planet known to have continents, although how they formed and evolved is unclear. The model being presented, especially in the next few slides, should add some clarity. Number 4. Sialic material, that is granite, granodiorite, and diorite, spreading over the Earth from the North Pole. Here we see emerging light sialic material, granite, granodiorite, diorite, floating on top of the peridotite at depth. Note that the current distribution of that emerging light sialic material is shown in green. Here we can see the emerging light sialic material, that is slag, moving southward. The movement, of course, would be in every direction from the North Pole. The black arrows show the internal migration of mantle material northward. This happens because of Rayleigh-Benard convection at spherical harmonic 1. This took place more than 4,000 million years ago, long before the Earth had a core. This red circle around the North Pole shows the emerging light sialic material moving southerly if the movement had been uniform, which it wasn't. Northern Canada and Greenland have not moved as far south. The sialic material moving southward from the North Pole would not move in straight lines as indicated here. The path of migrating light sialic material on a rotating Earth. The North Pole. Rotation of the Earth from the perspective of the North Pole, and the likely path of emerging sialic material. More than two-thirds of the landmass, the continents, on Earth is in the Northern Hemisphere. Why? We present a plausible answer to this question as we develop our model. However, we can't say at this stage the answer is intimately tied to spherical harmonics too. Spherical harmonics and the South Pole. At the South Pole, we find a negative gravity anomaly ranging in value from 100 to 200 milligauss. And like the North Pole, it is a major geophysical feature covering tens of thousands of square kilometers. Light sialic material converging at the South Pole. As Zhu et al. Have shown in 2021, the accretion of this slag-like material and the reworking of that material would eventually create a continent. And that accretion in the southern hemisphere eventually created the continent surrounding the South Pole. And as this image shows, only 32% of the southern half of the Earth is covered by continental slag-like material. This indicates that the accretion process in the southern hemisphere continued long after cessation of such processes in the northern hemisphere. This image shows that most of Antarctica is coincident with a negative 300 to 400 milligauss Bouguer gravity anomaly. We are now aware that Bouguer gravity anomalism is a measure of the density differences within the Earth. It is logical to conclude that the very large 500-kilometer negative gravity anomaly at the South Pole is due to a difference in density. The rocks there are slag-like granodiorites, diorites, and granites. A geological cross-section showing the 5,000 kilometer diameter accumulation of sialic material at the South Pole. And for the most part, that accumulation of sialic material coincides with the giant negative Bouguer gravity anomaly. Geomorphic features observed on a rotating Earth. The rotating Earth has created a clockwise rotation in the southern hemisphere. This movement has created the Scotia Sea, the southern tip of South America, trailing off to the east, creating the North Scotia Ridge, with the parallel Orkney-King George Ridge of Antarctica. This geomorphic feature is not unique. There are several other locations on Earth where parallel archipelagos can be seen. Here one can see the rapid rotation, clockwise rotation of Antarctica. The rotation rate can exceed 30 millimeters per year. Both the direction and intensity of this rotation of Antarctica certainly explains the Scotia Sea geomorphology. Here one can see the clockwise rotation of Antarctica in the southern hemisphere context. One of the problems solved in the creation of our current model, supporting our current model, is the rhyolite-basalt paradox. The rhyolite-basalt paradox refers to bimodal volcanism, a geological phenomenon where a single volcanic center erupts large volumes of both basalt, low silica, high iron magnesium, and rhyolite, high silica, low iron, low magnesium, but almost no intermediate composition lavas like andesite. Stilton 2022 suggests that there is a mechanical separation in the two magma types, where the two magma types may be stored in separate chambers or at different depths. Basalt often erupts around the edges of a system, while rhyolite erupts through the central fractures. The model we present here shows that not only do the two different rock types come from different chambers, they come from totally different locations. On the left is a solution to the rhyolite basalt paradox as presented by Stilton 2022 for the Yellowstone caldera. The right-hand image is our model showing the light sialic material, that is the rhyolite, forming at the surface of the Earth. This material emanated from the North Pole and has migrated southward to the Yellowstone region. We can see in this model that the basalt originates much deeper into the mantle, and the rhyolite magma is produced by crystallization and or melting of hybrid magmas. In other words, it is continental material. Number 6, continental shape. Most of the continents are tapered to the south. Most continents, excluding Antarctica, tend to be wedge-shaped. They're wider to the north and narrower to the south. Why? This can be explained inside of spherical harmonic 1. The geometry of the continents. Here we have pointed out some of the more obvious tapering and leads us into number 7 in our listing. Number 7. The Robinson-Orange Carpel model. Introducing the Robinson-Orange Carpel model. In the context of an orange, a carpel refers to one of the orange's naturally divided segments, which are the juicy compartments containing seeds and pulp. Here is the Robinson Orange Carpel model at sectorial harmonics 5, 5. This is the geoid visualization as an orange carpel-shaped sphere based on sectorial harmonic data. The alternating lobes map Earth's gravity anomalies, bulging ridges signifying stronger pull, while indented valleys mark weaker zones. Color gradients are from deep blue, low gravity, to red, high gravity. An important point to keep in mind that the orange carpel shape is a visual exaggeration of the minuscule variations in Earth's gravitational pull. As we have noted above, that minuscule variation in gravity intensity between the north and south poles of the Earth is only plus 400 to a minus 400 milligauss, total 800 milligauss. Milligauss is a unit of acceleration equivalent to 1/1,000,000th of the average value of the acceleration due to gravity at the Earth's surface. However, even though the variation in gravity intensity, that is only 800 milligauss in a million milligauss, is very small, the variation can have impact on the overall geometry of the Earth because it is taking place over millions, hundreds of millions of years. We have provided substantial evidence that whole Earth Rayleigh-Benard convection and spherical harmonic order 1 are synonymous. Since there's no real depth of discontinuity to a discontinuity, the name of spherical harmonic 1 is the diameter of the Earth. Numbers 8 and 9. 8. Gradual core formation terminated spherical harmonics 1. 9. Commencements of spherical harmonic 2. Spherical harmonic 2. The evidence for spherical harmonic 2. Number 1. Came into existence after the core formed. 2. Earth with two Rayleigh-Benard convection cells on diametrically opposite sides of the Earth. 3. Geoid residuals in the Atlantic and the Pacific Ocean on diametrically opposite sides of the Earth. 4. Coincide with large low shear velocity provinces, LLSVPs. To assist in visualizing these internal processes within the Earth, Boost 2006 has shown the lower order spherical harmonic response in respect to Rayleigh-Benard convection. In these whole Earth images, the gray area represents the Rayleigh-Benard plume coming from depth. The upper left-hand image represents spherical harmonic 2. Shishel and Smale 2001 presents substantial evidence through geoid residual altimetry anomalies in the Earth representing spherical harmonic 2. One of these geoid altimetry anomalies, shown here as a geoid residual center, is tucked in under the northwestern bulge of Africa. Alessandro Forte et al. 2010 presents supporting evidence for the location of this plumehead. This support is through SKS splitting and mantle flow at a depth of 250 kilometers. In seismology, SKS splitting refers to the phenomenon where shear waves, specifically SKS waves, split into two waves with different polarizations and travel times as they pass through anisotropic layers in the Earth's mantle. This splitting provides valuable information about the anisotropic properties and the deformation patterns of the Earth's mantle. In this presentation of the Atlantic-African superplume, the blue arrows represent the horizontal component of mantle flow predicted at a depth of 250 kilometers. One can see from SKS splitting that most of the mantle flow is divergent from the proposed plume head. And the other geoid altimetry anomaly, shown here as geoid residual center, is in the middle of the Pacific Ocean. We'll note that the spherical harmonic 2 image presented previously by Boos is orientated north-south. However, Shishel and Smale shows that spherical harmonic 2 is orientated east-west, coinciding with the equator of the Earth. As well, the spherical harmonic 2 geoid residual centers occur on exactly opposite points of the Earth along the equator. They are exactly 180 degrees longitude apart. There is considerable geological literature in the journals concerning the origin of the large low shear velocity provinces. One can see from the rotating image here of these provinces that much of the geoid residuals presented in the previous images coincide with these large low shear velocity provinces. Here is a different view of the same phenomena looking down directly onto the South Pole. This view lets us appreciate just how fragmented and broken the large low shear velocity provinces are. This figure indicates that the same time spherical harmonic 2, that is, Rayleigh-Benard convection on opposite sides of the Earth, was evolving, the Earth was also creating a core. Recall the evidence presented by Vaikalainen et al. In respect to the core, early Earth evolution of the core, and magnetic evidence for that evolution. As a reminder, Vaikalainen et al.'s research results are presented in the next slide. A reminder of magnetic evidence for this model. As Vaikalainen et al. State, quote, our study supports hypotheses of a strongly dipolar geomagnetic field in the early history of the Earth, possibly as a result of the absence of a solid inner core. Before moving on, some necessary definitions: mantle attenuation and seismic normal modes. Mantle attenuation describes how seismic energy is lost. primarily converted to heat, as waves propagate through the mantle. Seismic normal modes, the whole Earth free oscillations excited by larger earthquakes, provide one of the most powerful ways to measure this attenuation because they sample the entire planet at very long periods where scattering is minimal. How mantle attenuation is related to temperature and viscosity are presented in the following table. Note that mantle attenuation is designated by the letter Q, and this is the seismic quality factor, which quantifies anelastic attenuation in the Earth's mantle, representing the efficiency of energy propagation through the mantle materials. The most comprehensive presentation on the global 3D model of mantle attenuation using seismic normal modes is by Talavera Souza et al. Seismic tomographic models based only on wave velocities have limited ability to distinguish between a thermal or compositional origin for Earth's 3D structure. Complementing wave velocities with attenuation observations can make that distinction, which is fundamental for understanding mantle convection evolution. In this publication, they go on to say, quote, the nature of the LLSVPs, which we described earlier, is fundamental for understanding mantle convection evolution because a purely thermal anomaly will be short-lived, whereas compositional anomalies can form mantle anchors, influencing the pattern of mantle convection over long periods of time. The upper left-hand image is a model of mantle attenuation using seismic normal modes as presented by Talavera Souza et al. 2025. It is based on the standard accepted model of SP12RTS as created by Quellemeyer et al. 2016. The orange areas are negative anomalies, which means they are low attenuation, where seismic waves lose less energy. Mantle plumes produce low attenuation, that is, negative anomalies, as we can see here, because hot, partially molten mantle transmits long-period seismic waves with less energy loss. These two locations of negative mantle attenuation coincide with the geoid residuals, which, of course, coincide with the low shear velocity provinces. We have presented substantial evidence that spherical harmonic order 1 was terminated with the commencement of spherical harmonic 2. Spherical harmonic 2 is revealed by the presence of diametrically opposed geoid residuals on opposite sides of the Earth, as well as coincident LLSVPs. The LLSVPs were being created at the same time as the core, or immediately subsequent to the creation of the core. This process appears to have continued into the present and has prevented the formation of a discontinuity. Spherical harmonic 3. The evidence for the existence of spherical harmonic 3 is the sectorial harmonics of a polyhedral map projection and the natural longitudinal division of the Earth. The Dymaxion map, also known as a Fuller projection, is a polyhedral map projection created by R. Buckminster Fuller that projects Earth's surface onto an icosahedron. This projection is an attempt at solving the difficult problem of map distortion for other projections. Each face on the icosahedron would have similar scaling whether east-west or north-south. The very first thing that strikes me about this map is the natural division between various segments. There are three continental segments, the first incorporating North and South America, the second incorporating Europe and Africa, and the third segment incorporating Asia and Australia. The segmentation of the Earth as shown in the Dymaxion map should not be a surprise. Mapmakers for hundreds of years have been dividing the Earth into longitudinal segments, as we can see in this old world map. However, more recent geological evidence indicates that the right-hand side, that is, of this map, that is Africa, Asia, and Australia, is probably incorrect. And the Dymaxion segmentation presented above is more likely to be correct. We can see here that the eastern half of the previous map is divided into central and eastern. And the division between central and eastern is the Ural Mountains, which will be discussed in the next few slides. The Ural Mountains were formed approximately 250 to 300 million years ago during the late Paleozoic era through a massive tectonic collision. This event, known as the Uralian orogeny, involved the eastern edge of the Laurasia supercontinent colliding with the Kazakhstania continent, which is now part of western Siberia and Kazakhstan. The Ural Mountains run for 2,500 kilometers north-south through western Russia and form the boundary between Europe and Asia. One can see that there is a natural longitudinal division in the Earth. The question comes to mind, is this geometric arrangement due to sectorial spherical harmonic 3-3? This is the Robinson orange-carpal model at sectorial harmonic 3-3. Is there activity inside the longitudinal segments? When a mid-oceanic ridge is no longer, quote, mid-oceanic. Here is a mid-oceanic ridge that's no longer, quote, mid-oceanic. It's important to keep in mind that all movement on the sphere is relative. It is possible that the continental movement is negligible and the mid-oceanic ridge has migrated to the east, impinging on North American continent. This seems likely since observing the 0 to 30 million year ago distribution of rocks in the Pacific Ocean shows very broad distribution, while in the Atlantic it's very narrow. This indicates that expansion in the Pacific Ocean has been much faster than in the Atlantic. Is there a spherical harmonic 4? This view of Antarctica shows the fault systems totally surrounding that continent. This view also introduces the possibility of a fourth segment or carpel. Is the Pacific Ocean a segment without a continent? Is this geometric arrangement due to sectorial spherical harmonic 4-4? The Pacific segment is obviously devoid of the slag-like sialic material emanating from the North Pole. Could this lack of continental material in the Pacific be due simply to a blockage at the Bering Strait, which is between Russia and Alaska? Here on the Dymaxion map, we can see the Pacific segment going off to the southeast. Here we can see that spherical harmonic order 3 does not have a designated discontinuity at depth. It is the center of the Earth. However, spherical harmonic 4 does have a discontinuity at 5,150 kilometers and is called the Lehman 1 inner core, outer core discontinuity. Summary. Here we will scroll through the various patterns, bits of evidence that supports our model. In conclusion, what we are proposing here is that the spherical harmonic order is also an order of evolution, with spherical harmonic 1 having taken place at least 4,000 million years ago, and with the Earth becoming more ordered with time. That increase in order would manifest geophysically as the creation of new discontinuities within the mantle. If our model is a picture of reality, then one would expect that the most recent discontinuities that would evolve in the Earth would be the Conrad discontinuity at a depth of only 20 kilometers. Is this model possibly the beginning of a new way of thinking?